All right, hello folks, and welcome. Today we are going to take a look at finishing up our section 3.1 notes, and also our starting into section 3.2 as well. This is for Wednesday, September 16th. Okay, so like I said, we already started here with the derivative and the tangent line problem. This was from Monday or Tuesday, depending on when you had it. Okay, and we left off right here. Now, my class, we actually did this, and I wasn't supposed to, so you're going to get to see it twice. Hooray! Or you can also go skip through it, because that's the beauty of these videos. So anyway, another way that we can come up with the derivative via a limit is this form right here. Okay, where you'll notice again the f prime, right? That's what we know now is the derivative, okay? And then we have the limit as x approaches c of f of x minus f of c over x minus c. You'll notice then, because we have these c's here, this means we can only really use this method for, or we typically use this method for evaluating the derivative at a specific point c. Okay, this helps us find f prime of c. Okay, of course, provided this limit exists. The existence of the limit in this alternative form requires that the one-sided limits of limit as x approaches c from the left of f of x minus f of c over x minus c, and the right-hand limit there also exists. And then they're the same, of course, because that's what a limit requires, right? The left and right-hand limit are the same. These one-sided limits then are also called the derivatives from the left and from the right. Okay, so when we look at example 2 from earlier in the notes, so that's up here. Okay, this right here with the quadratic and evaluating it at x squared plus 1, or evaluating the function x squared plus 1, the derivative of it at those 2 points. Okay, we can use this definition as well to evaluate that. Okay, so again, remember that the function was, I'll write that here for you, rather than have to scroll back and forth, x squared plus 1, and we'll just do it at the negative 1, 2. We won't do it at the other point, the 0, 1. Okay. So let's, again, evaluate f prime of 1 using this alternative definition here. So our c then is going to be this 1, and so it's the limit as x approaches 1 of f of x minus f of 1 over x minus 1. Okay? Of course, we know what f of x is, we know what f of 1 is, because we have our function right there. So limit as x approaches 1 of x squared plus 1 minus f of 1, which is 1 squared is 1 plus 1 is 2 over x minus 1. And now we just simplify. This becomes negative 1. And then we can factor and cancel. Don't forget to write the limit every step until you actually do the direct substitution here. Okay, and so that equals the limit as x approaches 1 of x plus 1. Plugging in the 1, now a direct substitution we can perform, gives us the 2, which is what we got in the earlier problem, right? We go back up to example 2. There it is. Okay. Oops, we got negative 2. I made an error somewhere. There should be a negative 2 here as well, right? Okay, so let me go back down here. Let's see. X minus 1, x plus 1, 1. Oh, because we're going to negative 1, so this should be a negative 1, negative 1, negative 1, negative 1. And so when I plug in negative 1 here, that would give me 0. And that's still not right. Where did I make my mistake here? All right, let's figure this out here. Oh, because I also evaluated this incorrectly. That should be a negative 1, so this should not be a 2. Oh, no, it'd still be a 2, sorry. But this should be minus x squared plus 1 is your function, minus f of negative 1. But that's still, oh, here we go. And that's minus a negative 1 down here. There it is. So this is plus 1. So these wouldn't cancel. It would be these that cancel. So you have an x minus 1 there. Okay, there we go. Sorry about that. And so then when I plug the negative 1 minus 1, we get the negative 2. Okay, which does match what we got earlier. If I now go back up, example 2, there it is, negative 2, right, when we evaluate that negative 1, 2. Okay, alternative definition, right? So remember that -2, that then indicates that the slope of f of x at x equals -2 is, at x equals -1, that was the y coordinate, the x coordinate there, at -1 is -2. Okay, and so there's our value there. All right, moving on. So we also want to discuss the idea about differentiability and continuity. So being able to differentiate something and checking out the continuity of a function as well. There is a relationship between when a function is differentiable and whether a function is continuous or not. Okay, right? They both deal with limits and stuff like that. So let's take a look. We're going to sketch a graph of each function and then determine the intervals in which the function is continuous and the intervals in which the functions are differentiable. Okay, now we haven't talked about how to determine when something's differentiable, but we'll get to that here once we, get into the problem. So let's graph 1 over x. So if you remember 1 over x looks something like this. Okay, I'm going to do a really rough sketch there of it. Okay, very important now too, because we have that new way to describe a derivative as f prime, right? Very subtle difference between f and f prime. So when you're looking at a graph, make sure that you are sure about what graph you're looking at. Since I have f of x here, it's the original function, right? But if you see a little apostrophe there after the f, that means you're looking at f prime, the derivative. And we will have situations where we're going to look at the derivative of a function, not just the original function. Okay, so let's determine the intervals in which the function is continuous, right? So just looking at this, right, and knowing our function here, we know that the f is continuous where? From -infinity to 0, union 0 to infinity, right? That's our interval there. Okay, so where is it not continuous? Well, it's not continuous at x equals 0 because there is a vertical asymptote there. Well, actually, you know what? Let's do it even better. Let's say because the limit as x approaches 0 of 1 over x does not exist. Okay, so now let's examine the differentiability of this. So that means we want to look at the derivative of 1 over x. Okay, so we'll have to take its derivative here, which did we do earlier? 1 over x? We did 2 over t, but not 1 over x. Okay, we'll do 1 over x here real quick then. So we'll take the limit as delta x approaches 0 of f of x plus delta x minus f of x all over delta x. Okay, and so again we use the 1 over x here, so we have the limit as delta x approaches 0 of 1 over x plus delta x minus 1 over x all over delta x. And then we got to combine these things here in the numerator, so we'll get a common denominator. We'll multiply the top and bottom by x over x here. And we'll multiply the top and bottom here by x plus delta x over x plus delta x. So this results in x over x times x plus delta x minus, and then x plus delta x over x times x plus delta x, like that. And it's all over delta x, like so. Okay? So now, taking a look here at the functions, so combining here, so it's going to be x minus an x. So the x's are actually going to cancel. Actually, do this in a different color. Do it in blue. So the x's are going to cancel because x minus x, but it's a minus at delta x. So we'll have the limit as delta x approaches 0 of negative delta x over x times x plus delta x, and then instead of dividing by delta x, I'll multiply by 1 over delta x there. Okay, let me see if I can do this better. All right. Scoot down just slightly. Okay, there we go. So the delta x's will cancel, and so that leaves us the limit as delta x approaches 0 of negative 1 over x times x plus delta x. Okay, which when I plug in 0 then gives me, because now I can direct substitute, I'll get negative 1 over x times x plus 0, which is negative 1 over x squared. So there's the derivative, right? That is f prime of x. Now, let's examine this, right? Where will this be discontinuous? Well, this is discontinuous when x equals 0, right? We don't want x to be 0, which means then, since it's the derivative of f, f is not differentiable at 0, right? Since our derivative has a problem at 0, that means the original function is not able to be differentiated at 0. Okay, so while we are continuous for this answer right here, okay, so we can also then say f is not differentiable. Again, the derivative is not continuous, right? Is not differentiable at x equals 0. Okay, so, or we'll say is differentiable because it wants us to discuss whether they are differentiable. So f is differentiable, we'll say. Actually, you know what? Do this. Let's see if I can. Okay, well, that doesn't quite work there, but all right, I'll just do this. Yeah. Okay, is differentiable for negative infinity to 0, union 0 to infinity. Because any other x value has no problem for that derivative, right? You can plug any other x value in there that you want, just 0 would cause a problem. So we're going to exclude that from where we are differentiable. Okay, so let's talk about number 2. All right, absolute value of x minus 2 plus 1. So again, the absolute value graph, right, is a v, okay, but we're shifted right to an up 1. So 1, 2, 1, so we'll say right there. And then it's going to go kind of up 1 to the right, like that, and then up 1, left 1, like that. Ooh. Okay, voila, there's our graph. There's f of x. Now, let's take a look at our continuity. Where is this thing continuous? Continuous everywhere, right? So we'll say f is continuous from negative infinity to infinity. Okay, and there's no problems, right? Any x value there is not a problem. So we can just say, I'll say all real numbers, that kind of stuff too. Now, what about its derivative though? Okay, this is where it gets a little bit tricky. How do you take the derivative of the absolute value? Well, we don't. Okay, if you want to try and take the derivative of the absolute value here, what we would have to do is we want to rewrite the absolute value as a piecewise function. Remember that, what does the absolute value do? Okay, so for when this here is, when x minus 2 is positive, right, it stays the same. So, you know, if we want, oops, sorry. So for x values that are, you know, in this case, well, when is x minus 2 positive? When is x minus 2 greater than 0? When is it positive, right? So we can add 2 to both sides, and it's when x is greater than 2. All right, so for x values greater than 2, evaluating this is just like evaluating x minus 2 plus 1, right? Because you don't have to make anything the opposite there. If x is greater than 2, then that x minus 2 will still be positive, and so we don't have to worry about, you know, changing any signs. However, if x minus 2 is less than 0, in other words, if this quantity here is negative, then we have to do the opposite, right? So, whoops. So for here, and we'll just include the negative 2 as well. Actually, you know what? I'm going to include the 2 here, and not the negative 2, sorry, 2. Okay. Then we want to do the opposite of what's inside here. So it's going to be negative x plus 2, and then the plus 1. Right? And that's how you can create a piecewise function from a given absolute value function. Okay? You just keep one of them, keep one of these pieces the same, right? There's x minus 2 plus 1, and it's for values when x is greater than or equal to 2. And again, we got this 2 because we want this x minus 2 to be positive. So we set x minus 2 to be greater than 0, solved for 2, or solved it, they got 2, and so then that creates this scenario right here. Okay? However, when x minus 2 is less than 0, that means it's going to be negative, right? That's where x value is less than 2, which is where we got this from. Then we need this to be the exact opposite of what it is. So it's negative x plus 2 plus 1. Okay, and yeah, you can simplify this if you want to just be negative x plus 3 over x minus 1, like that. Okay? So, what does this mean for us? Right, so the derivative then, well, we can just take the derivative of the individual pieces here, right? And so, just, well, they're lines, right? So this line right here, it's got a slope of -1, so I can just go ahead and say it's just -1, right? And this is a line as well, it's got a slope of +1, so I can go ahead and say that's +1. And the constraints say the same. So look at our derivative here, right? Imagine graphing that. We have a y value of -1 whenever x values are less than 2, but we have a y value of +1 whenever x values are greater than or equal to 2. So we have a jump discontinuity here, right? Actually, let me just do it right here. Okay, so what it's going to look like is, for x values less than 2, we're going to be here at -1, open circle, and then fill it in circle right here, and then like that. And that's our derivative. So jump discontinuity means we are not differentiable. So f is not differentiable at x equals 2. Or in other words, since we want to know when they are differentiable, for -infinity to 2, union 2 to infinity. Woo. Whoa again. Okay, there you go. Okay, just like so. Okay. All right, so, excuse me, just type this in here real quick. Okay, sorry about that. Let's continue on down here. All right, same thing here for a -1/3. All right, so let's go on here. Or for 1/3, I mean, actually 1/3. Okay, oh, so sorry, I wanted to note here then. So how can we kind of see that we're going to have a problem here up in this curve? Well, you can see that we're suddenly changing slopes, right? We suddenly change from a -1 slope to a +1 slope here, right? The slope of this piece, it's a line, the slope is down 1, right 1, -1. The slope here is +1, so our derivative then is going to suddenly change. Okay, so sudden change in slope, not gradual, right? It just suddenly jumps from -1 to 2. Okay, and that comes whenever you see like a sharp point on f of x. Okay, this sharp point right here, it happens because you have a sudden change from a -1 slope to a +1 slope. Okay, where else? Well, let's look at x to the 1/3. Okay, now if I graph this, it's going to look something like this. Ooh. Nope. Okay, something like that. Okay, so where is this function continuous? We'll say that's f of x. Function is continuous from -infinity to infinity, right? No problems here. No problems whatsoever. Okay, so where is it not differentiable? Well, I'm not going to take the derivative this time. Let's just take a look at the graph. All right, so looking at the graph here, right, we can see that it looks like all these slopes are going to be pretty easy to find, you know, for the most part along the graph there. What happens at 0? Okay, it's maybe not so obvious because of the way I drew it. Maybe the better way for me to draw would be something like this. Okay, looks like it might get a little vertical in there, which is an undefined slope, which would mean the derivative would be undefined, therefore not exist. So how do we figure that out? Well, again, let's ask the question, is this thing differentiable at 0? So we can find that by using our previous definition, right? So f prime of 0 equals that alternative definition, right? Limit as x approaches 0 of f of x minus f of 0 over x minus 0. Okay, and so limit x approaches 0, f of x is x to the 1/3. F of 0 is 0 over, and then x minus 0 is just x. And so x to the 1/3 divided by x is x to the -2/3, right? You subtract the exponents there, the 1/3 and the 1. and which is really then 1 over x to the positive 2/3. And if I do a direct substitution of 0 in there, what are we going to get? It'll be undefined. So sure enough, we do have a vertical slope there right at 0. Okay, so what does that mean? F is differentiable oof, there you go. Oh no, that was bad. I deleted too much stuff. There we go. Differentiable on the interval here. Negative infinity to 0. Whoops. Union 0 to infinity. Okay, and so that's the best we can say. Let's circle this without making a huge mess. Okay, there it goes, and there's f is continuous right there. Okay, so what do we see? Well, this here we have a vertical tangent. Okay, so vertical tangents means that our derivative does not exist at that point. There we go. Okay, because that's an undefined slope. All right, let's take a look at number 4 then. So number 4, all right, we can see we have a line and a parabola in our piecewise function here. So again, I'm going to kind of like just So x squared for x values that are greater than or equal to 1. So right here, and then 2, 4 right here, and then on up like that. Something like that. Yeah, not quite. There you go, something like that. Okay, maybe that's better. All right, and then the line, 3 minus 2x, so 3, oh, less, sorry, 1, it would be 1. So we do join up there. Okay, that's good. Something like that. Okay, for x values that are less than 1. So there's a piecewise function. Line, parabola. Okay, so again, since these piecewise functions join up, right, if I plug 1 into here, and if I plug 1 into here, they join up, right, they have the same y value of 1. So the function then, if this is f, right, f is continuous on interval there from negative infinity to infinity, right? Completely continuous. Individual pieces are okay, and where they join up is okay too. Differentiability. Well, again, we can look at this and see what the derivative is going to be, right? What's the slope of this line? It's negative 2. Okay, so we have a negative 2 slope, and then what's the slope of this thing going to be? Well, it's changing, right? So do they join up? Well, it looks like, again, we want to check where they join up and see what's going on here. So let's again do that limit as x approaches 1 from the left of f of x. Oh, well, we're going to do the derivative, sorry. So it'll be f of x minus f of 1 over x minus 1 kind of thing. Okay? Which is then going to be the limit. Actually, you know what? Let me just make this even easier. I'll go ahead and put the function in. There you go. Because again, we're approaching 1 from the left, so that's using the linear function here. Okay, and then f of 1, I can go ahead and plug that in. Again, from the left, if I plug 1 in now, it's going to be 1. Okay, so simplifying here, 3 minus 1 is 2, so we'll have 2 minus 2x over x minus 1, which if I factor out a negative 2 from this, I'll have x minus 1. So cancel those out, and we get a slope of negative 2. Even there's no place to direct substitute, so we just get our slope as negative 2. Okay, from the left, right? From the left. That's our slope of our tangent line right there. Which again, no surprises, it's a linear function. All right, now let's take the limit as x approaches 1 from the right. And in this case, we're going to use f of x as the x squared there. Okay, minus f of 1. So plugging in 1 there is going to give me a 1 again. And then over again, x minus 1. Well, the numerator factors. Again, we have to use these one-sided limits because of the piecewise, right? one piece is to the left of 1, one piece is to the right of 1. And again, the individual functions look like they're differentiable everywhere, right? This slope is always going to be -2 because it's just a line. And this parabola here, this tangent line slope, looks like we got plenty of tangent lines, you know, kind of thing, no problem there. The only issue maybe is where they join up. So let's see what happens with factor. Okay, cancel. Plug in the 1, we get 2. Uh-oh. Okay, where we join up here, the left and right hand limits disagree. Okay, so the left hand and right hand derivatives of f at x equals 1 disagree, or you could say aren't equal. So f is differentiable from -infinity to 1 union 1 to infinity, and the best we can do. Okay. And again, you can kind of see it's kind of pointy there, right? Which leads us back to what we saw earlier, here with the absolute value. Okay, it's a sudden change in slope. In this case, we're suddenly changing from -2 from the left to +2 from the right, and there's no smooth transition, which means we're jumping on our derivatives graph. Okay, so theorem: if f is differentiable at x equals c, then f is blank at x equals c. So we just talked about comparing differentiability and continuity. So let's go back through here and look at this, right? So here, f was not continuous at 0 and not differentiable at 0. Okay, so not continuous, not differentiable, both at the same point. Here, though, f was continuous everywhere, but then f was not differentiable at 2. So here it seemed like continuity and differentiability, right? Not continuous at 0, not differentiable at 0. It seemed like it paired up. But then when we go down here, we see that we are not differentiable at 2, but we were continuous at 2. So they don't quite pair up. Let's see what else, though. Here we can see not differentiable at 0, and again, still continuous at 0. Okay. And then here we can see not differentiable at 1 and continuous at 1. So it looks like continuity doesn't necessarily affect differentiability, but in fact differentiability does affect continuity. It does tell us about continuity. If the function is differentiable at x equals c, we will know that the function is also continuous at x equals c. Okay, if you look here, each one of these differentiabilities, -infinity to 1, 1 to infinity, that was also included in here. Now, continuous also was continuous at 1, right? But if it was differentiable at a certain region, -infinity to 1, 1 to infinity, then it was guaranteed to be continuous in that same interval too. I shouldn't say region, I should say interval. Okay? Same thing here, right? Differentiable from -infinity to 0, 0 to infinity, that was included in here. Okay? Differentiable from -infinity to 2 to infinity, that was included in here. Differentiable from -infinity to 0, 0 to infinity, and exactly continuous at the same point too. So differentiability implies continuity, but not the other way around, right? Continuous from -infinity to infinity, not differentiable everywhere, right? Not at 2. So be careful about that. Okay, so in summary, okay, if a function is, again, differentiable at x equals c, then it is continuous, right? That's what we just talked about. It is possible, though, right, and this is also what I was trying to mention, it is possible for a function to be continuous at x equals c and not be differentiable. Okay, so it's a one-way only. Differentiability implies continuity. Continuity does not imply necessarily differentiability. Okay, Could they both be could they be continuous and differential at the same point? Yes. But just because you know something's continuous does not mean it's differentiable there. But if it is differentiable, guaranteed to also be continuous. All right. Let's take a look at example 5 here. All right, and answer some questions. So we're going to graph this piecewise function and determine some answers. Okay, and determine some answers to some questions. So let's do that. So I'll do this in blue here. So. All right, maybe I'll do this in colors, right? We'll do some colors here. So I'll do actually, you know what, no, I'll do this, okay. I'll do the absolute value of x in green. I'll do this one in like a light blue, okay, light blue. I don't know if that really stands out that much. And then we'll do this one in like orange here. Really make your eyes bleed, okay? So, all right, green first. Ooh, did I pick this green? I think I picked that green, okay. So absolute value of x for x values less than 2. So here's 2, so at 2, absolute value of 2 is 2, so put an open circle, and then fill it in, -1, 1, 2, 2, like that, and we'll go down. That, and then back up. Okay, on to infinity. All right, and then we'll do the light blue, and that's the -1/2 x plus 3 for 2 less than or equal to x less than 6. So at 2, that'll be 2. So 2, 2, we're filled in there. That's nice. Okay, and then down 1, right 2. Down 1, right 1, 2, and that's at the 6. That's open circle there. Okay, and then we'll go to the orange. And from 6 onward, okay, it's -1/2 x. For x values greater than or equal to 6. So at 6, 2, 3, 4, 5, 6, yep, -1/2 times that will be -3. So filled in dot. I'm going to go down 1, right 2, and on down that way. Okay, and so this is the entire graph of f of x right here. This is f of x. Okay? So let's determine some stuff. A, find all values of x such that f is continuous. So again, at any point here, you can pause the video, do it on your own. So this is a good idea, right? Why don't you stop here and try some of these on your own right now? Do these problems. I got the graph for you. Go ahead and answer the questions. Okay. So find all values of x such that f is continuous, right? We can see here everything kind of joined up nicely, but right here we have a discontinuity. So f is continuous, we'll say. -infinity to 6 union 6 to infinity, like that. Okay. Find the limit as h approaches 0 of f of 1 plus h minus f of 1 all over h. Do you recognize what this is? Okay, think about this. Instead of h's, right, pretend that those h's are delta x's. Right, like that. Now recognize it. 1 plus delta x. It's the definition of the derivative, right? Limit definition of the derivative. And specifically, we're evaluating the derivative at 1, right? So we just want to find the derivative at 1 here. Okay? Oh, sorry, not at 1. Excuse me. At 0. No, at 1. Sorry. The x value is 1, right? Okay, this is where the x values would be right here. So at 1. All right, so we can look right here. There's x value of 1, right? You can maybe just look at it and tell. What's the slope right there? It's a linear equation. Well, it's part of a linear equation, right? The absolute value is 2 linear equations, really. Okay, what's the slope at this point? We're going up 1, right 1, right? So you could just say it's 1. Okay. Alternatively, you can also, try and like evaluate this as well, but it's 1. Okay. So again, remember that this is the difference quotient. Right? No, well, it's the limit definition of the derivative, really. So I should just say that. Yeah. And again, it was at x equals 1. And I knew it was the 1 because x equals 1 because this replaced the x's, right? These are only x's right here, and the 1 replaced that. So we're evaluating the derivative at 1. And again, I'm just using the slope of the curve here. I'm just looking at the slope of the curve. It's linear, so a slope of 1. Okay? All right. How about f prime of 4? Well, again, 1, 2, 1, 2, 3, 4, okay, we're on this right here. Okay, what's the slope here? It's also a line, right? Whoops, erased too much. There you go. It's also a line. And what's the slope? -1/2. So this would be -1/2. Okay, you could use limit definition of the derivative there if you wanted to, but we just know the slope. We just know the slope at 4 is -1/2 because that's the part of the graph that we're on right there. Okay. Or you can also say or a slope of the tangent line. Okay. How about this one? Okay, we're approaching 0 from the left now, so we're going to find the derivative, but from the left at 6. All right. So here's 1, 2, 3, 4, 5. There's 6 from the left. That means we are going to evaluate the derivative from this function, right? From that side. From that side, we're using this piece of the function. What's the slope there? Again, it's a limit definition of the derivative, right? You can see it looks just like this, except we're at 6 now. Okay. It's going to be that -1/2 again. Okay. We're approaching this. So again, you think this is the slope of f approaching 6 from the left. Okay, which is linear. But now we approach 6 from the right. Well, now we're approaching from the right. That's this piece, right? What's the slope of that? Still -1/2. Okay, so the slope of f approaching 6 from the right. Okay. So moving on here then. Letter F then. Find all values of x such that f is differentiable. All right, so looking up here, okay, where are we not going to be differentiable? Well, see a point right here, right? So not differentiable at 0. Where else is it pointy? We're suddenly changing from a +1 slope to a -1/2 slope. So again, right here as well is going to be a problem. So 2. Okay, and then where else? Right here. Okay, even though the slopes do line up, right? The slope there is -1/2. The slope there is +1/2. The function's not differentiable. Okay, we're not continuous here. Okay, and so when you talk about differentiability, implying continuity, there's a logically equivalent statement called the contrapositive. So when you say a statement like this, if this, then this, a logically equivalent statement is if not continuous, if f not continuous at x equals c, then f is not differentiable. At x equals c. Okay, so these two statements are logically equivalent. They have the same truth to them. So since the first one here is true, this one as well is the same. Okay, so while we can't say if something is continuous, it's differentiable, we can say if something is not continuous, then we know it's not differentiable. Here we are not continuous, so we're also not differentiable there at 6. So where's differentiable? At, or I'll say on, well, we'll just do the interval. From -∞ to 0, union 0 to 2, union 2 to 6, and then, whoops, no parentheses, or no comma there, union 6 to infinity. Okay, and again, at 0 point, sudden change in slope from -1 to +1. Okay, at 2 point, right, pointy part of the graph, sudden change from a slope of 1 to a slope of -1/2. And then here, discontinuous, so therefore differential, or not differentiable too. Okay, so there's your differentiability. Boom, 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 boom. All right, I would say questions on that, but there's no one here to talk to. So if you have questions, make sure you reach out to your teacher then. All right, all right. Let's continue on then, because we are going to do some basic differentiation rules here. We're going to talk about the constant rule. Okay, so obviously that limit definition of the derivative is like pretty unwieldy, right? It's a lot to like try and calculate these limit definitions of the derivative, right? To like do all this mess. Whoa, this mess right here, right? That's a lot. There are shortcuts, and we're going to show you those now. For those who took pre-calculus with like Thompson or Miss Blumen, and Mr. Thompson, Miss Blumen, then you probably saw some of these, but bear with me here. So the constant rule, right? So we're going to use the definition of the derivative or knowledge of the graph to find the derivative of y equals 7. Okay, so let's graph y equals 7. Actually, I'll use blue here yet. Okay, so y equals 7. So 1, 2, 3. Well, you get the idea. It's going to be a horizontal line like this through 7. Okay, see, there's 7 right there. Okay. So what's the slope of this line? The slope is 0, right? It's horizontal. Therefore, the derivative at any point along here will be what? If the slope of this line anywhere is 0, the derivative will also be 0. Okay? So y prime will be 0. Or you could also say, dy dx equals 0. Okay? So, because again, the slope of this line is 0. So, what do you think is going to be true about any time we have a function equal to a number? Right? Y equals 10, y equals 11, y equals 12. All those slopes will be 0, so their derivatives will all be 0. So the derivative of a constant is 0. Okay? Now, let's take a look at the power rule here. Okay? And what I would like you guys to do is to pause this video and to take the derivative of this, take the derivative of this, take the derivative of this, using the limit definition of the derivative. Okay, we're going to try and come up with a shortcut here when we have powers, like the x to the third, the x to the 2, and the x to the 1/2 there. Okay, so go ahead and do that. Pause the video and try it. Okay, hopefully you tried the video, or you tried it, so I'm going to try and squeeze it in here too, because this can be kind of crazy. So, okay, so it'll be x plus delta x cubed minus x to the third all over delta x. And so if I expand this out, let's see here, it'll be x to the third plus 3x squared delta x plus 3x delta x squared plus delta x to the third. If you don't believe me, that's what it does expand out to. You can do it on your own by doing, x plus delta x times x plus delta x times x plus delta x. If you really want to, you would FOIL this out, okay, get your answer, and then distribute this through as well, kind of thing, okay? Pretty crazy. But that's what it would FOIL out to be. Multiply it out to be, and we do that right there, and all over delta x. So what cancels? X cubed and x cubed. All these other terms here have a delta x. So let's factor out a delta x. 3x squared plus 3x delta x plus delta x squared all over delta x. These delta x's cancel. And so we're left with just this. Now you can direct substitute into 0, but there's a delta x here, there's a delta x here, so those are all gone. And so what do we end up with? 3x squared. Okay, so whoops, equals 3x squared. Okay, so that is f prime of x. All right, do the same thing here for g of x. So it'll be x plus delta x squared minus x squared all over delta x. And so if I expand this out, right, it'll be x squared plus 2x delta x plus delta x squared minus x squared, and minus x squared, right, that's where that came from, all over delta x. X squareds cancel. And we get, oh, and I can factor out a delta x, right? So the x squared is canceled. Leaving behind this, I can factor out a delta x there. All over delta x. Delta x is canceled, and now, since those canceled, I can plug in 0 for that delta x, and I get 2x. So g prime equals 2x. And again, this is because we start with g, so this becomes g prime. Okay. Last one. Okay. So this one's going to be limit as delta x approaches 0 of x plus delta x to the 1/2 minus x to the 1/2 all over delta x. Okay, we have those square roots, right? Remember what we do with those? Multiply by the conjugate. So times x plus delta x to the 1/2 plus x to the 1/2 all over the same thing. Okay, and so that leaves us the limit as x approaches 0 of, this will be x plus delta x minus x, right? Again, the middle term is going to cancel because you're going to multiply those two things together, and you're going to multiply these two things together, and they'll be the exact opposite, so they cancel. When we multiply these two together, right, they're the exact same, but they're both the 1/2, so it becomes this to the 1, or just, this right here, like you see. Ooh. Okay, and then negative x to the 1/2 times positive x to the 1/2 will become this minus x. So that's all over delta x there. Okay, and then times the x plus delta x to the 1/2 plus x to the 1/2, like that. Okay, as you can see here, what's going to happen? These x's will cancel. And now the delta x's will cancel, leaving a 1 up here. And so I can now plug in this 0. So I'll have h prime of x equal to 1 over x plus 0 will be x. So it's x to the 1/2 plus an x to the 1/2, 2x to the 1/2. Or 1 over 2x to the negative 1/2. So do we see a relationship here between these derivatives and their original functions? X cubed becomes 3x squared. X squared becomes 2x, or 2x to the 1, if you like. X to the 1/2 becomes 1/2 x to the negative 1/2. Do you see the pattern? What happens? When you take the derivative of a variable like x to a power, you bring that power out front, multiply it with the x, and then lower the power by 1. Okay? So the derivative with respect to x of x to the n is n times x to the n minus 1. And that is another derivative rule. So now we have two derivative rules. Derivative of a constant, 0. Derivative of something of x to a power, n times x to the n minus 1. Okay? So again, the power comes out front, and then you lower this power by 1. So 3x squared. Okay? So use the derivative rules to find the derivative of each of the following. Pause the video, try it on your own. Use those two derivative rules we just came up with. Remember that it was helpful here to rewrite that square root of x as x to the 1/2. So use your constant rule, use your power rule to answer these questions. Go ahead and do A, B, and C. All right, hopefully you paused the video. If you didn't, shame on you. Pause it now. Do it. Okay, here we go. All right, so the derivative of this, f prime of x, which rule are we going to use here? Well, we have something to a power, right? So this is just a power rule. So it becomes 2 times pi to the 1, right? No, 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 no. Pi is a constant. Pi is a number, right? And when you square a number, it's still a number. So when you take the derivative of pi squared, it's like taking the derivative of 3 or 4, okay? This is just 0. Okay? No power rule there. Tricky, tricky. I know, that was me. All right, so next one. Cube root of t. That's really t to the 1/3. So again, rewrite any of these cube roots as rational exponents. This is why you were, forced to do this kind of thing with your previous math classes. Now that we have this, right, it's the power rule, right? It's that power rule that we have right there. So 1/3 t, 1/3 comes out front, right, like that. And we lower this power by 1. What's 1/3 take away 1? negative 2 over 3. Okay, if you like, you could rewrite this as 1 over 3t to the 2/3, or if you really like, you could write 1 over 3, and then you do like the cube root of t squared or something. Okay, all of these are acceptable answers. Last one here. What's this one? We have a constant in the numerator. We have a power in the denominator. Can I just say like then this is going to be, whoops, not that. Then h prime of x will be like 0 over 2x, like that? No. Okay. Again, we can't combine our rules like that. If you're going to think of this as like a quotient of two individual things, we have a separate rule called the quotient rule that will allow us to simplify that. No. The best we can do right here is to rewrite this as x to the negative 2. Now it fits our power rule. Before, this does not fit our power rule. We only can do this if we have x to a power, right? Right up here, x to a power. So now when I rewrite it, it's x to a power. And I can say then h prime of x equals negative 2 x to the negative 3. Or negative 2 over x to the 3rd if you like. Okay? There we go. All right, let's continue on here. Good gracious. Oh yeah, we stop here. I'll give the derivatives. Okay, I got 2 more pages. Well, this page and the next page. Okay. Find the equation of the tangent line to the graph of y equals x squared when x is negative 2. Okay, again, the main question. What do we need to write the equation of a line? Well, we like to use point-slope form, right? We are going to put away our old habits of slope-intercept form. We're going to use point-slope form, so that means we need to know a point and we need to know a slope. Let's focus on the point first. We know that x is negative 2, but for a point, we need a y-coordinate too. Well, that point for the tangent line is on our graph too, right? It's the point where the tangent line intersects the graph. So this coordinate negative 2 will also be on our graph. So we can just plug that negative 2 in. So negative 2 squared will give us a positive 4. So again, I'm just plugging that negative 2 in for the x there. And then we excuse me, and then we get that y value 4. So there's our point. We still need the slope. How do we find the slope of a tangent line? The derivative. So we're going to take the derivative of y equals x squared. So power rule, right? Y prime equals 2x to the 1, or just 2 to the x. Sorry, 2 times x. We're going to then plug in our point, and that'll give us our slope. So we're going to take this and we'll evaluate it at the point negative 2, 4. But of course, there's no y-coordinate, so really we just need to evaluate it at the x-coordinate of negative 2. And so that gives us negative 4. Okay, so there's our slope, because that's, again, the value of the derivative at the point of tangency, at the tangent point, right? And then there's, there's our point. And so let's write the equation of the line. Y minus 4 equals negative 4 times x minus negative 2, or you can just say x plus 2 if you like there. And there's our answer. Okay? All right, constant multiple rule. So we're going to use the definition of the derivative to find the derivative of this. Okay, so here we go. Quickly going to do this. So what happens, so you can see here what's the issue, right? We could just take the derivative of x squared, but we have this 3 in front. What's that going to do to our derivative? Well, let's find out. So again, I'll quickly do this. 3x plus delta x squared minus 3x squared all over delta x. So I'll go ahead and expand this out and distribute 3. So it'll be 3x squared plus 6x delta x plus 3 delta x squared minus 3x squared all over delta x. Okay, again, I was expanding this out and distributing the 3 through. That gives us this. Okay, so the 3x squareds cancel, so I'll go ahead and erase those. Goodbye, goodbye. And then everything else has a delta x left over, so I can factor out a delta x here. So let me do that. Right, and the delta x's cancel. So we have 6x plus 3 delta x. Plug the 0 in for delta x. So that's going to be gone, and we'll have just 6x. So, or 3 times 2x. So do you see what happened here? Since we have this constant multiple in front, taking the derivative is the same thing as leaving that constant multiple and taking the derivative of the individual piece, x squared, and then just remultiplying your answer, right? So what's the derivative of x squared? 2x, and then we just multiply with the 3. Okay, so 6x is the ultimate answer there. So constant multiple coefficient rule. If f is a differential function and c is a real number, the derivative of a function c times f of x is c times f prime of x. Just like that. Or in other words, the derivative with respect to x of c times f of x, c times f prime of x. Okay, again, I would pause here for questions, but there's no one to ask any questions, so we'll just go down here. Go ahead and try examples 6, A and B. Okay, you may have to rewrite if necessary to our appropriate forms. Okay, hopefully you paused the video and did that. So rewriting here, you should have 4/5 t to the third. That's a good way to rewrite that to get it in the correct like constant multiple form. And so that 3 will multiply out front, so it becomes 12/5, and then this reduces by 1, so it's t squared. And there's our answer, the derivative. Wow. Or you could do the limit definition, your choice. Okay, a of k, we're just changing the variables up on here, so don't freak out, right? It's just literally 3 pi over 2 times k to the negative 1, right? K is our variable, so I'm going to bring that out front here, but since it's in the denominator, we have to put that k to the negative 1. 3 pi over 2 is just a constant. So we can kind of, again, ignore this piece. We really just want to take the derivative of this. So a prime of k will be 3 pi over 2 times negative k to the negative 2, like that. And then we can recombine here and get negative 3 pi over 2 k to the negative 2. And there's our derivative. Okay? All right, last rules. Sum and difference. The derivative of the sum or difference of two differentiable functions is differentiable as well. And the sum or difference of their derivatives is, guess what? Just the individual pieces. Okay, the plus or minus is in there for if you have addition or subtraction. Okay, so in other words, if you take the derivative of a sum or difference of differentiable functions, then that's the same as just taking the derivative of the individual pieces and then adding and subtracting them back together. Okay, so in other words, let's find the derivative of each of the following here. So we're just going to consider each one of these individually, right? Break them up over addition, subtraction. Break them up over addition, subtraction here. We'll talk about C in a second. And then just take the derivative. So f prime of x. What's the derivative of x cubed? Well, that's just going to become 3x squared. Okay. What's the derivative of 4x? Well, that just becomes 4. But there's a minus there, so I'm going to bring down the minus sign. And then what's the derivative of 5? Well, that's just 0. So minus 0, or you can just get rid of it there, right? And so there's your derivative. Okay. R, let's rewrite that first before we do this. So it'll be theta to the 3/4 minus, and this also will be helpful if we rewrite that. 5 over 2 theta to the negative 3. And this one, I'll rewrite a little bit there, minus 1/2 theta to the 4th. Try and move this over some too, maybe. Okay. So then, take the derivative, right? R prime equals 3/4 theta. And we have to subtract 1 from that negative 3, from that 3/4, so we get negative 1/4. Minus, but it's going to be negative 3 times 5 halves, so it becomes plus 15 halves theta. Subtract 1 from negative 3, negative 4. Okay, and then finally right here, bring that 4 out, so it'll be 4 times 1/2, which will be 2 theta to the 3. And there's your derivative right there. Okay, and then I'm going to make some room here for C. So for C, we want to rewrite this, right? So since we're dividing by t, we'll just divide each one of these things by t first. We'll go ahead and also say that this square root of t is t to the 1/2, like so. And so we'll end up with h of t. Again, I'm not taking the derivative yet, I'm just rewriting. So be careful with that too. Some students think that in the process of rewriting, they now have taken the derivative. Okay, be careful. No, this is just rewrite. Okay, so we're going to rewrite. Okay, so this becomes 3t squared plus 5t minus, and then t to the 1/2 divided by t is t to the negative 1/2. Okay, now be careful here. We did get rid of that divide by t, so technically these two things are not equal when t is 0. So I'm going to put like a little just caveat here, right? T not equal to 0. Because here t would be 0 over 0, and here you can plug 0 in no problem. Okay, so anyway, now let's take the derivative. So 3t squared. 2 times 3 is 6t. Derivative of 5t, 5. Derivative of negative t to the negative 1/2, positive, right, because it's a negative times a negative, positive 1/2 t to the negative 3/2. Because again, if it's negative 1/2, you subtract 1, negative 3/2 is your fraction. Yes, there's going to be fraction arithmetic here, okay, so you'll need to be able to be comfortable with doing fraction arithmetic, but there is your derivative. Okay, thanks for watching, guys. If you have any questions, please reach out to me or Mr. Goff, and we'll be happy to help you out. Have a good day.